Yeah, thank you very much for the introduction. Thank you very much for the opportunity to come to Iceland and to present my work. I want to do something that Kevin Buzzard would also accept. So in my system, Naproche, I try to do a little bit of the perfectoid spaces project, but it's just about perfectoid rings. What are perfectoid rings? They come up in these perfectoid spaces. And here is a definition. And you see that it's a ring. A perfectoid ring is a certain ring which satisfies a number of extra axioms. So what we'll see is we start from topological ring axioms, and then there are more and more specializations until we run into this. Along such a long definition, you have to justify certain things, well-defined conditions, and so that is what has to be proved along the way. Well, in the end, we get in the system Naproche to a definition which looks like this. P is perfectoid if R is complete and uniform, and so on. So compare with the upstairs original definition from a Peter Scholze paper, and there are quite close similarities, and it is written in natural or semi-natural language. So let me say a little bit about the Naproche system. It accepts, proof checks text in a natural language. It's a controlled natural language, which is given by some grammar. This controlled natural language stems from previous projects, mainly the SAD project by Andrei Paskevich and his co-workers, and the language is Fortel formula theory language. In the Naproche system, this has been altered a bit so that you can input things in LaTeX, and then you can also typeset your formalizations, and they should look like mathematical articles. And you've seen a little bit of such typesetting on the slide before. The whole thing that I did is something nearly 50 pages of text. This is a, well, fully formal text if you look at these grayish parts of it. So that is really in the Fortel input language, in the formal language, typeset in LaTeX. And then around the gray parts are the literate parts, the commentary parts to explain what's going on. So these are pages 47 and 48. And on 48, you see there is this definition of perfectoid that I showed you, and it ends with that. So again, I'm somebody who has gone through the definitions one by one, following actually the original lean formalization and translate it. But I don't give an example of a perfectoid space. I don't develop any further theory here. So the Naproche system is quite a standard proof assistance system, only that the second bar here is then a controlled natural language for mathematics, this Fortel, which is sort of the intermediate language here. So this is designed very much in the direction of naturalness of proof texts. So here's this controlled natural language defined by a formal grammar. And what you are aiming for are readable formalizations in LaTeX format, and also LaTeX tricks or macros are being used. So some things in the original formalization are macros which are interpreted in one direction as some first order identifier, and on the other hand, they can be interpreted by the typesetting as something calligraphic on your screen. We use, as I said, a literate style where we have the strict formalization and the surrounding explanatory text. We use strong ATPs like E or vampire to bridge proof steps, because part of naturalness is not just using natural language, but using it sparsely. Yeah? You want to leave out most of your intermediate steps, and these intermediate steps we leave to the ATP. The whole thing, the whole system, can be used within the Isabelle Prover IDE, which gives a nice environment for editing and checking, but we are not connected to the logic of Isabelle in any way. Okay, the motivation, as I said, was the lean formalization of perfectoid spaces by Kevin Buzzard, by Johan, and by Patrick Massot. And in the sort of general page about this, you see this, and upstairs is their definition, their lean definition of perfectoid rings as part of the story. And now I want to give you some idea of the mathematics, but as I said, my mathematical idea is, okay, there are rings, and we have to put more and more conditions on them for whatever reason. My guiding example are formal power series of certain kinds, but I can't exhibit to you a ring which is really perfectoid here. So we are using these Laurent series-like things just as to give you some idea what is going on in this sequence of definitions. A main concept here is the idea of boundedness, to be bounded within a topological ring. And you can see, if you look at this definition 240, so I take just snippets from the Naproche formalization here, because it's so normal mathematics-like that I hope I can use these kinds of explanatory text here. Okay, so it's a boundedness in an epsilon delta way, you could say. Yeah? Talking about neighborhoods instead of epsilons or deltas, but so it's a rather normal topological way of saying that something is small. And then you want more boundedness, so this power boundedness comes in. You want that the powers of an element are all, well, give a bounded set, so that you would call power bounded. And if you want to, this one, if you want to sort of continue this example of the power series, you see that you have boundedness if you say my series have to start at a fixed n0. So this could even be minus 200. But then if you look at this definition and compare and so on, even that would be bounded. Only the whole thing, where the n can be anything, you can start at any negative exponent, that would not be bounded. So the ring is not bounded, but all these nice sub-rings there, or subsets, they are nicely bounded. And also, if you think about power boundedness, where you want that your exponents get larger and larger if you do the successive powers here, because then in the let's say the norm and metric that we have here, you get smaller and smaller. You see the 2 to the minus, and there is then this exponent thing of the f minus g. So if you have something like which only start as with x to the 1000, then you are thinking of things like 2 to the minus 1000. So things get smaller and smaller, like in decimal numbers, the further out you go to the right. Okay, so let's continue on this idea of boundedness. We put all the things that are power bounded together in some RO, and this ring, this should be a subring, and indeed it is, if we are in a non-Archimedean situation, which we would be in this power series. But of course, these power series are just sort of a hint, a crutch or so, to have some idea of what's going on. Okay, so it goes on like that. We say when something is non-Archimedean, this ring is non-Archimedean, and then we specialize further that a Huber ring is one which has a sort of rather special topology on it, where the topology is given in an algebraic way, but actually these power series still can be used as at least to illustrate these definitions here. Yeah, so we are in that realm, but we are expressing things abstractly, and then taking all these abstractions together in the end, we should reach our desired definition. Then something which is also to do with boundedness and being small is nilpotency. Here we look at a topological nilpotencies where things, their powers tend to 0 instead of just being bounded. They should even tend to 0 here. And so again, for example, X, the power series which just has this one element X to the 1 here, this is nilpotent because it goes out and out. So it's like 0.1 in the decimals, and that is sort of going to 0 in its powers. And then the X is also a unit, and such units, these nilpotent units, they are called pseudo-uniformizers. And so we have something like that. A ring with a pseudo-uniformizer, so we could still do this in these formal power series, would then be called a Tate ring. And we are nearly there. So if we have these kinds of rings, then there's something interesting, namely this Frobenius map. I hope one can see something here. Yes, right. So if we go to P's power, where P is a chosen prime number, then this, in let's say modulo P situations, would give you a homomorphism here. And the big question is whether this Frobenius mapping, whether this mapping on certain quotients here would not just be a homomorphism, which you can prove, but it would also be an isomorphism. Yeah, so R is perfectoid, and it's all relative to this fixed prime number P. R is perfectoid if it is complete. This means topologically complete. It should be uniform, meaning that this R0 or R upper O, actually it was, that was also a bounded subset and subring. And then we have this pseudo-uniformizer, but it should satisfy certain extra property, namely a divisibility. Its P's power should divide the pi, this prime number P here, within the subring, and you want this isomorphism here. Okay, so whatever this is good for, this is the definition of perfectoid. And let me indicate some of the aspects of the formalization and compare it to the lean formalization. Yeah, we saw the lean formalization already in this snippet from this lean website here. Now we see some more lean here, for example, the boundedness that we discussed, and which was the central notion here. How does that come out? Well, we already saw the boundedness as a definition, as a sort of natural text definition. And both these formalizations draw, in this case, on a text by Wedhorn. And I think we are, with Naproche, pretty close to the Wedhorn original. Then, of course, it's about proofs, and there is a big difference. On the lean side, you see these imperative proofs, do this macro, do that macro, And on the Naproche side, we try to stay in this, let's say, epsilon delta or standard topological approach. And I think the proof on the right-hand side has a different kind of structure and readability than on the left-hand side, which is also true for larger proofs here. For example, if we want to show that this R upper O is a subring, we have to show that with the addition, we would stay within the subring. And the proof, when it's written out in Naproche, is, well, it's not a complete one. You see the dot, dot, dots here, but it's sort of a standard undergrad exercise approach to that. Okay, we need basics, we need preliminaries. In Lean, we would import from the existing library, and we would also see there some extra imports for things which probably in the end, I don't know, exactly ended up also in MathLib. So Lean has a big basis of already done mathematics on which you would build, and you are also supposed to build on it so that it's a sort of a big mathematical universe that you are building up. Here we are doing our own content, so this is taken from the formalization, and you see from the very basics here, sets, natural numbers, and so we go on and end with topological rings as preliminaries, and then we can start what I showed to you. So these preliminaries also have to be introduced in the Naproche style. Here, natural numbers, very basic. It gets more complicated if we go to structures, but we take also a very simplistic approach. So we have defined before what an additive group is, and then we just say a ring is an additive group, but we have to add further axioms to it, which we do there in terms of these arithmetic properties of rings. So this is not a good way in general to do structures, mathematical structures. But as this is sort of its own theory here, it's all sort of just written for the purpose here, we can do certain shortcuts like mathematicians also like to do in their papers. It's all in first order. So we build up a first order universe here, which has certain sub-sorts, defined sorts. Our sorts or types are defined by first order formulas or are introduced axiomatically. So you build up this kind of this picture here. Yeah? So we have objects here on the right-hand side. Some of these objects would be natural numbers. That is this egg here in the middle. We also, set theory, talk about classes, but then, as we know from Russell, not all classes can be sets. And so this is, here are the sets. We declare that the natural numbers also are a set in the natural numbers. So this kind of first order build up is what is behind our formalization. So if we go through the two approaches here, we see that Lean anyway was the original here, and I'm just sort of copying a short initial segment up to the perfectoid rings from the Lean original here. So the Lean is big. This is just a subset. In Lean, you build on the Lean foundations like MathLib and what is built deeper into Lean as well. We here have basically ad hoc preliminaries. And this is saying the same thing again. So you have a big Lean theory, and our approach is rather little theory approach. Yeah, I want to do some mathematics. I take these axioms today. Maybe tomorrow I take some other axioms to talk about groups and rings. And the technical term in formal mathematics sometimes has been the little theory approach. Of course, we do use different logics. Instead of dependent type theory, I use first order logic, but these dependency of sorts and soft types here, you can easily also model in first order logic, and you would, of course, model it by type guards. The Lean language is rather a computer language and really is a computer language, whereas we are using this controlled natural language. On the Lean side, okay, there are different styles, but let's say it's mostly these tactic proofs, whereas we really emphasize declarative proofs. And then a lot of proof details should be left implicit and to ATPs. On the Lean side, you have very efficient proof checking, seconds or so. And here on my side, there's a heavy use of ATPs, just like using sledgehammers all the time. And so the formalization that I'm talking about, it took half an hour on a standard laptop. But of course, you could improve it if you sort of put in more, let's say, engineering effort by caching things and so on. And so some further projects should reduce these enormous checking times. So, okay, on the Lean side, you have a fully developed, wonderful world, language world and mathematical world. On my side, it's just very experimental, and I'm just exploring whether one can do natural language proof checking. And I think up to a degree, the latter is possible. Fully formal mathematics appears possible within a traditional format of writing and proving. It's an open question. The answer is probably no, because I can't do it myself and I'm retired. And so what should I do? Can Naproche be extended to a big system with a universal axiomatic foundation and a big library whilst preserving naturalness? Yeah, it probably could, but whether this is realistic, I don't know. Surely the work on Naproche will have to be continued, and a main thing is really the efficiency of proof checking, because if you want to work interactively and you're confronted with these enormous checking times, it's a real pain. Another interesting question is whether the natural language approach can be applied in other circumstances as well. Big systems like Lean. And of course, these days, one would also ask whether some of the language trouble that we have can be done by language models. Okay, I would like to thank you for your attention. And here are some links. So with these links, you can find this formalization. So my talk is not quite over yet. This formalization should have been in Isabel 2025, but then there was a hiccup with naming of folders because Windows, or let's rather say DOS, wouldn't accept certain names, but this only came out after this was checked in the final stages of the preparation of Isabel 2025, and we couldn't fix it so quickly. So if you go to this line here, there is sort of an intermediate 2025 version of Isabel which has this formalization in it. So if you load that and click yourself through to the perfectoid rings, you will find it, or you will find the formalization which would work in 2024's Isabel. You would find that with using the upstairs links there. Okay, now let's say thank you for your attention.